After studying this module, you shall be able to know the various types of carbanions, learn the features of carbanions, learn the stability of carbanion, identify different types of reaction involved in the formation of carbanions, learn the reactivity of carbanions. First of all, I will give you a brief introduction about carbanions. Heterolytic cleavage of a bond where carbon retains both the shared pair of electrons results into the formation of a carbanion, that is, a carbon atom having negative charge. In these species, carbon atom carrying negative charge has 8 electrons in the valence shell, 6 from the 3 covalent bonds and 2 from lone pair of electrons. The basic form of carbanion is methide ion, CH3-. It is a carbanion of methane, CH4, which is formed by loss of proton hydrogen ion H+. CH4 after losing H+ forms CH3- methide ion, which is a carbanion. Nucleophilic carbon species are required to form new carbon-carbon bonds. Carbanions are known to be good nucleophiles. Thus, carbanions are important in chemical synthesis as intermediates and thus they are used in the preparation of other substances. Carbanions are used for making important industrial products such as plastics. Stable carbanions do exist. In 1984, Olmsted synthesized lithium crown ether salt of the triphenyl methane carbanion. It was obtained by adding N-butyl lithium to triphenyl methane in tetrahydrofurane at low temperature, followed by addition of 12 ground 4. So, a triphenyl methane carbanion was obtained. Next, we will see how carbanions are generated, that is the generation of carbanion. Carbanions are generated as intermediate in various organic reactions. Some of the methods for the generation of carbanion are proton abstraction, decarboxylation, addition of nucleophile to alkene, formation of organometallic compounds. First, let us see how via proton abstraction carbanion is generated. When proton is abstracted from a carbon center, then the resulting anion is called carbanion. For example, if an alkane like RH gives proton, a carbanion is generated R-. The acidic hydrogen of an organic substrate can be abstracted by an appropriate base. For example, carbanion generated from the carbonyl compounds. Here are some examples showing generation of carbanion by the abstraction of acidic proton using a base like OH-, NH2-, RO-, that is hydroxide, amide or alkoxide. If a alpha hydrogen containing ketone is treated with amide, the alpha hydrogen, which is acidic, is abstracted by the amide and a carbanion is generated. Similarly, other carbanion containing compounds like esters, anhydrite or alpha-cyanoesters, from their alpha hydrogen can be abstracted using a base and we get carbanions. Nitroalkanes have acidic alpha hydrogen and that can also be abstracted using a base and a carbanion can be generated from them. The next method for generation of carbanion is decarboxylation. Decarboxylation of carboxylates leads to the formation of carbanion intermediate. For example, RCOO- loses CO2 molecule and R- the carbanion is generated. Other method for generation of carbanion is by the addition of nucleophiles to alkene. Carbanion are generated by the attack of nucleophiles on one of the carbon of an alkene. It results into the development of negative charge on the other carbon. A nucleophile like Y- can attack the alkene and a carbanion can be generated on alkene itself. Another method for generation of carbanions is during the formation of organometallic compounds. Metals which are less electronegative than carbon, such as magnesium, lithium, potassium, sodium, zinc, mercury, lead, thallium, they react with alkyl halides under appropriate conditions to form a carbon-metal bond where the carbon carries negative charge and metal positive charge. Although the carbon does not carry full negative charge, but it acts like a carbanion in its reactions. Thus, metallation reverses the polarity of the carbon from positive in the reactant to negative in the organometallic compound. This is known as en blanc. For example, alkyl bromides react with magnesium in the presence of dry diethyl ether to form alkyl magnesium halides, which are also known as Grignard reagent. As you can see in this reaction, RBr reacts with magnesium to form RMgBr. Magnesium being electropositive acquires partial positive charge and consequently the alkyl group carries a negative charge, thus acts like a carbanion. Reaction of alkyl halides with lithium also form alkyl lithium with negative charge on carbanion. Reaction of acetylene with sodium in liquid ammonia results in the formation of sodium acetylide. CH triple bond CH acetylene, when treated with sodium liquid ammonia, the acetic hydrogen is abstracted and sodium acetylide CH triple bond C minus Na plus is formed, where you can see the carbon has negative charge, so it's a carbanion. Halides also contain carbanion-like species. Halides are generated by the reaction of triphenyl phosphine with alkyl halides. These are also carbanion-like species, such as, let us see, triphenyl phosphine PPH3 when treated with methyl bromide forms a intermediate triphenyl phosphonium methyl bromide, which on reaction with butyl lithium forms a carbanion CH2 minus. The halide, the carbon which is attached to phosphorus has negative charge. So this halide also has a carbanion like species. Dithiones are generated by the reaction of propane thiol with carbonyl compounds. The dithiones, when further treated with butyl lithiums, gives a dithione anion in which the carbon has a negative charge. So dithiones can also be used for the generation of carbanion. We can also generate carbanions of weak CH acid. The fluoride ion has the ability to cleave a proton from those CH acids whose pKa value ranges from 20 to 28 and forms carbanions of weak CH acids. For example, phenylacetylene, when treated with 1 molar solution of tetraammonium fluoride TEAF in acetonitrile, it forms phenylacetylene ion. C6H5CH, when treated with tetrafluethyl ammonium fluoride, is giving C6H5C triple bond C minus, which is carbanion. Carbanions having chiral centers are also known. Such chiral carbanions can be generated from a chiral substrate. Here in this example, you can see a chiral substrate having S configuration when treated with N-butyl lithium gives a carbanion species in which the carbon carrying negative charge is chiral. Next, let us discuss the features of carbanion. Carbanion possess an unshared pair of electrons, thus It is an electron-rich molecule. Carbanion has octet of electron in the outer shell. The negatively charged carbon is trivalent. If all the substituents on the negatively charged carbon are different, the carbanion will be chiral. Carbanion acts as a base or nucleophile. Carbanion has pyramidal geometry. Carbanion undergoes rapid interconversion between two pyramidal forms. The energy barrier is different for different types of carbanions. For example, for a methyl carbanion, the energy barrier is 2 kilocalorie per mole, while for trifluoromethyl carbanion, value is around 120 kilocalorie per mole. The higher energy barrier for trifluoromethyl carbanion is due to the more electronegativity of fluorine atom, which is more stabilizing than a hydrogen atom. Here you can see if R is equal to H, then it is a methyl carbanion and the inversion to is 2 kilocalorie per mole, while if it is fluorine, the trifluoromethyl carbanion has 120 kilocalorie inversion barrier. The negatively charged saturated carbon atom is sp3 hybridized in case of carbanion. The lone pair of electrons occupy one of the sp3 hybrid orbitals. Since the lone pair bond pair repulsions are expected to be greater than bond pair repulsions, the bond angles in carbanions are much less than regular tetrahedral angle, which is 109 degree 28 minute. In other words, carbanions do not have regular tetrahedral geometry but have pyramidal structure in which bond angles are in between 97 degree and 100 degree. The stability order of alkyl carbanions is methyl much greater than primary carbanion, which in turn is much greater than secondary, and then tertiary carbanions are least stable. Stable bridgehead carbanions are also known. So next we will see the stability of carbanion, that is the factors which contributes towards the stability of carbanion. The factors which can stabilize or disperse the negative charge on carbon will stabilize a carbanion. So the stability of carbanion depends on the following factors. One is inductive effect. The next factor is extent of conjugation of the anion. Hybridization of the charge bearing atom is another significant factor which decides the stability. Aromaticity also leads to stability of carbanions. First, we will discuss the inductive effect, that is how inductive effect decides the stability of carbanion. If the groups which are attached to carbanion are electron releasing in nature, they will increase the negative charge on carbanion on the carbon and thus destabilize it. However, electronegative atom or electron withdrawing groups adjacent to the negatively charged carbon will stabilize the carbanion. The alkyl groups which are electron releasing in nature and due to their inductive effect, that is the plus I effect, will decrease the stability of carbanion. So more the number of alkyl groups attached, lesser will be the stability. Carbanions prefer a lesser degree of alkyl substitution. Therefore, the order of stability of alkyl carbanions is methyl most stable, then primary, then secondary, and the least stable is a tertiary carbanion. Presence of electronegative atoms like fluorine, chlorine, bromine or other electron withdrawing groups like nitro, cyano, carboxylic, carbonyl close to the negatively charged carbon will stabilize the charge. Thus, more the number of such groups in a carbanion, greater will be the stability. As you can see, CH3 minus is least stable as it has 3 hydrogens attached to the carbon, whereas if the hydrogens are replaced by fluorine atoms successively, the trifluoromethyl carbanion is the most stable as it has 3 fluorine groups attached to the carbon which are electronegative. Now we will study the next factor on which the stability of a carbanion depends. This is extent of conjugation of the anion. If negatively charged carbon is in conjugation with a double bond, the resonance effect will stabilize the anion by spreading out the charge by rearranging the electron pairs. So, if you are asked which is more stable amongst benzyl and allyl carbanion, the answer will be the negative charge is delocalized through resonance in both benzyl and allyl anions. So, which will be more stable? That is the question. Here we will see that benzyl anion has more number of contributing structures. Thus, it is the benzyl anion which is more stable than allyl anion. Resonance in some carbanions is shown here. As you can see, enolate of ketone which is generated by the abstraction of alpha hydrogen of carbonyl compound is also resonance stabilized, and the carbanion has a enolate canonical form. Similarly, enolates of ester, malonic ester, acetoacetic ester, cyanoacetic ester also have their resonating structures. So, these are resonance stabilized carbanions. The nitronate anion which is formed by the abstraction of alpha hydrogen of alkane is also resonance stabilized. Another factor which decides the stability of a carbanion is the hybridization of the charge bearing atom, that is the hybridization of that carbon which is negatively charged. Stability of anion will depend upon the S character of carbanion. That is, more the S character, higher will be the stability of anion. The percentage S character in hybrid orbitals is such that 50% in case of sp hybridized, S character is 33% in sp2 hybrid orbitals, and S character is 25% in case of sp3 hybridized orbitals. Carbanion generated from alkyne is much more stable than the carbanion from an alkene and then from an alkane. As the carbanion generated from the terminal alkyne, the carbon has greater S character. Here you can see the ethite carbanion, ethenite carbanion and acetylide carbanion, they differ in the carbon hybridization of the carbon bearing negative charge. In case of ethite carbanion, this carbon is sp3 hybridized. In ethenite carbanion, the negatively charged carbon is sp2 hybridized. The acetylide carbanion has sp hybrid carbon which is negatively charged. Therefore, the stability order will be acetylide will be the most stable, being maximum or most S character. It has 50% S character of the carbon bearing negative charge. The ethenite carbanion has 33% S character. Therefore, it is less stable, and the least stable amongst these three is the ethite carbanion, in which the carbon has sp3 hybridization and least S character. So, if you are asked to explain the order of stability of propargyl anion, propionyl anion and propyl anion, we can explain it similarly on the basis of their hybridization. So, here is the answer. In propargyl anion, the triply bonded carbon is sp hybridized. In case of propionyl anion, the doubly bonded carbon is sp2 hybridized, while in propyl anion the carbon is sp3 hybridized. Orbital with greater s character is more close to the nucleus and feels more nuclear charge. The sp hybridized atom has 50% s character, are more electronegative than sp2, which have 33% s character, and sp3 hybrid orbitals have 25% s character. The distance of lone pair and nucleus is less if the lone pair is sp hybridized than in a sp2 hybrid orbital, since it is more favorable for the negative charge of an anion to be in an orbital close to the positively charged nucleus. Therefore, sp hybrid anion is more stable than sp2. As you can see, the stability order will be propyl carbanion least, then propionyl is more stable, and the propargyl carbanion is the most stable amongst these. So, we could answer this question on the basis of the hybridization. Next, we will see how aromaticity decides the stability of a carbanion. In some carbanions, the lone pair of electrons of the negative charge is involved in delocalization to add on to the aromatic character of the molecule, which gives them extra stability. For example, in cyclopentadienyl anion, there are 6 pi electron and thus it obeys Huckel rule, the 4n plus 2 pi electron rule. It has pKa value 16 and the anion is stabilized by aromatization. Cyclooctatetraene on reaction with potassium gets converted to cyclooctatetraenyl dianion potassium salt. Now, this potassium salt is a type 10 pi electron system which is stable due to aromaticity. Now, let us further study the reactivity of carbanion. We know that carbocations are strong Lewis acids while carbanions are strong bases. Carbanions are part of most of the common reaction types such as displacement, elimination, condensation, addition, rearrangement, polymerization, etc. First, we will discuss displacement reactions. Carbanion can combine with positive species in a displacement reaction. Here you can see a carbanion reacting with a Lewis acid and the carbon attacks the proton and the conjugate base is released. Elimination reactions also involve carbanion formation. In a conjugate base elimination reaction, even Cb, the CH bond breaks with the formation of carbanion as intermediate. The developed negative charge on carbon assists in the loss of leaving group, leading to the formation of alkene. Another type of reactions where carbanions are involved are the condensation reactions. First, we will see aldol condensation. Reaction of aldehydes or ketones to give beta hydroxycarbonyl compounds is known as aldol reaction. The reaction can be base or acid catalyzed. The base catalyzed reaction is more common. In a base catalyzed reaction, the carbonyl compound is deprotonated at the alpha carbon by base like alkali hydroxides to give carbanion, which is resonance stabilized with its enolate form. The next step is the nucleophilic attack of the carbanion to the carbonyl group of another non-enolized aldehyde molecule. The product which is obtained after workup is a beta hydroxyaldehyde or ketone. Here you can see acetaldehyde in presence of base gives a carbanion in which the alpha hydrogen is abstracted. This carbanion attacks the CO group of another carbonyl to give an intermediate which then gives a beta hydroxyaldehyde which is known as aldol. Next, let us see another type of condensation reaction which involves formation of carbanion. This is Claisen condensation. Formation of beta ketoester from carboxylic esters is known as Claisen ester condensation. The mechanism involves the formation of carbanion from the ester by reaction with a base. Here you can see ethyl acetate when treated with ethoxide ion generates a carbanion after abstraction of the alpha proton. This carbanion generated can add to another ester molecule. The resulting anionic species results into beta ketoester by loss of an alkoxide anion. So, Claisen ester condensation giving ethyl acetoacetate from ethyl acetate is also involving formation of carbanion. Next, condensation reaction which again involves a carbanion is the Dickmann condensation. This reaction is also given by esters. It is an intramolecular condensation of diesters to give cyclic beta ketoester. The base abstracts alpha proton to one of the ester group to form a carbanion. The carbanion then undergoes nucleophilic attack at the carbonyl carbon of other ester group present within the same molecule. The product obtained is a cyclic ketone. This cyclic ketone is also a beta ketoester. Thus, all these condensation reactions, aldol condensation, Claisen condensation, Dickmann condensation involves carbanion formation. Next type of reaction which involve carbanion formation are addition reaction. In this, first we will discuss Michael reaction. Addition of carbanion to an alpha beta unsaturated carbonyl compound is known as Michael reaction or Michael addition. As you can see, the active hydrogen of ethyl acetoacetate when abstracted by a base generates a carbanion. This carbanionic species can attack the beta carbon of alpha beta unsaturated carbonyl compound to give the product. Next type of reactions which involve carbanion formation are the rearrangement reactions. In this, we will discuss Feverovsky rearrangement. The rearrangement of cyclopropanones and alpha haloketones in the presence of base to carboxylic acid derivatives is known as Feverovsky rearrangement. For example, in cyclic alpha haloketones, reaction involved abstraction of alpha proton by base to give a carbanion intermediate which is resonance stabilized with its enolate form. This carbanion or enolate cyclizes to a cyclopropanone intermediate which is then attacked by the hydroxide nucleophile to form carboxylate derivative. Anionic polymerization reactions also involve carbanion formation. Polymerization involving anionic intermediates are known. For example, anionic polymerization of styrene in presence of soda amide proceeds with the formation of a carbanion intermediate in the chain initiation and chain propagation steps. Soda amide dissociates to give sodium ion and amide anion. The amide anion attacks styrene to generate a carbanion. The carbanion intermediates attacks another styrene molecule to propagate the chain. Repeat. Next, let us see Wittig reaction. This reaction also involves carbanion formation. In a Wittig reaction, alkene or olefins are formed by the reaction of phosphonium halides with aldehyde or ketones. The halides have carbanion character. Here you can see the triphenyl phosphine methylide halide has CH2 group in which the carbon is negatively charged. This reacts with aldehyde or ketone to form a cyclic intermediate betaine, which then gives the resulting alkene. Dithiene or amplong also involve carbanion formation. Dithiene on reaction with butyl lithium gives an anion which reacts with alkyl halides. This on subsequent hydrolysis gives carbonyl compound. The dithiene after loss or reaction with butyl lithium forms an intermediate in which the carbon which is between the two sulfur atoms is negatively charged. So this carbanion reacts with alkyl halides to form an intermediate which on hydrolysis it is giving an aldehyde. Some other important reactions which involve carbanion intermediate are Claisen-Schmidt reaction, benzoin condensation, Perkin reaction, Mannich reaction, malonic acid synthesis, acetoacetic acid synthesis. Now, let us summarize what we have studied till now. Heterolytic cleavage of a bond with shared pair of electrons on carbon gives a carbanion, and the carbanion has pyramidal geometry. The factors which affect stability of carbanions are inductive effect, extent of conjugation of the anion, hybridization of the charge bearing atom, aromaticity. Carbanions are part of most of the common reaction types such as displacement, elimination, condensation, addition, rearrangement, polymerization, etc. Some examples of reactions involving carbanion intermediate are aldol condensation, Claisen condensation, Favorowski rearrangement, Wittig reaction, benzoin condensation, Perkin reaction, Mannich reaction.